like that I uploaded?
You see, I know
Is it
it's also
helpful?
I just wanted to like try it out. I was curious.
All right, so let's get it started. Do you guys remember what we did last time? We talked about position, we talked about velocity, we talked about acceleration, right? And then we started to talk about the relationship between them. So a little bit of review on what we have done. So we had the position as S, and then we had V and acceleration. Do you guys remember what is V? How we can get V from S? Yeah, you can answer right away. So it's the derivative, ds dt, right? And how we get the acceleration? dv dt. So basically, we differentiate once to get velocity, and then we differentiate another time to get the acceleration, right? So we also can write this as the second derivative of the position with respect to time, right? What if we want the velocity from the acceleration? What we are going to do? The reverse process of the differentiation is integration, right? So I need to integrate once the acceleration with respect to dt to get the velocity. And if we want to get the position from the velocity, I want to integrate the velocity with respect to the time, right? So that's basically what we have done the whole entire lecture. And then we got a bunch of equations, if you guys remember. The first equation was, I believe number one was S minus S node with the integration of V dt from T node to T, and actually that's what we did here. And then the second equation was that the V, and then I said that V from the integration from A, yeah, I believe it was like V minus V node is the integration from T node to T A dt. By the way, all the equations, did you guys check the documents that I uploaded last time? There is the equation sheet. I have them in two sheets, but it's better that you print them on the same page. Okay, so in the first part, you will have chapter 2, particle motion, and then you will have the general equation, VA, and then you will have the non-constant and the constant acceleration. So that's what all you need in the exam, or in a test, or in a quiz. That's the equation that you need. So basically, let's check the equation that I have here, right? Yeah, V minus V node is the integration. Number 3, I'm gonna write the equation number 3 here, which if you guys remember, it was based on ADS equal VDD. We got this equation last time, and then we integrated it, and we got that you have V squared minus V node squared equal to the integration of ADS, and this is from S node to S. Do you guys remember why I couldn't take the velocity out of the integration, or the acceleration out of the integration, or the acceleration out of the integration here in these three equations?
If they weren't constant.
Because it was variable acceleration. The acceleration wasn't constant. If it's constant, we will come up with another 3 different equations, which are S minus S node is going to be equal to V node T minus T node plus half A node T minus T node all squared. And then the second equation, V minus V node, so A node T minus T node. And the third equation is going to be V squared minus V node squared to A node S minus S node. So all what you have to do, you have all the equations that you need, but you have to decide what equations that perfectly fit for solving the problem. Like, let's say I give you in your problem velocity and acceleration, and I didn't give you any time. This equation doesn't have any time. You don't need time of the motion to solve this equation. So that's perfect for this. But let's say I give you time. If I give you time, I have to look at these two. Okay, so that's something that you need to think about. If I told you in the problem that it's a variable acceleration, but I'm not going to tell you directly it's a variable acceleration, you have to figure it out yourself. So if you figure it out yourself and find out that it's a variable acceleration, so you'll have to use this. If you find out that it's a constant acceleration, so you'll have to use this. So let's solve a problem in the textbook that we are using, which is Hepler. All right, so this problem, let's put it here in case the camera doesn't catch the auto 40. All right, I have a car, and this car moved from origin O. Let's say, I'm gonna say this car is something like this. And here it says the car on the left in the photo moves in a straight line such that, by the way, it's a straight line, because we're gonna, in a little bit, we're gonna deal with curved path and all of these. So I'm saying it's a straight line, and such that for a short time, its velocity is defined v equal to t squared plus 2t, where t is the time in seconds, and this is feet per second velocity. Determine its position and acceleration, so we need the position and acceleration when t equal to 3 seconds. I also gave you at t equals 0, s equal to 0. That means this car starts from rest. Velocity was 0, displacement was 0, at time equal to 0. You tell me, is this a variable acceleration, and I'm going to use these equations, or is it a constant acceleration, I'm going to use this equation?
Variable.
Why it's variable?
Time.
Because velocity is function in time, and if I want to get the acceleration, I have to differentiate this with respect to t, and it's going to be function in time. That means the acceleration is function in time. How? V is equal to this. If I want to get A is dv dt, right? So if I differentiate this with respect to the time, what I'm going to get here? Can you differentiate this with respect to time? T?
6t plus 2.
It's going to be 6t plus 2, right? Is that variable acceleration or constant acceleration? It's a variable because it's function in t. Every second it keeps increasing. All right, so I have the acceleration, and I also want, so the acceleration is very easy. I always like differentiation because it's very easy to do. But integration is a little bit harder. How can I get s? So I have v. To get acceleration from velocity, I differentiate. To get displacement from velocity, what should I do? I have to differentiate v with respect to t, right? That's what I have here, this equation, right? But since I have s node is equal to 0 and t node is equal to 0, it's fine to write it that way. But if you want to put the full equation, I can say s minus s node, the integration from t node to t. I know that this is equal to 0, so s is going to be the integration from 0 to t of the velocity 3t squared plus 2t, and all this is dt. Can you integrate this function?
t cubed plus
T
t
cubed,
squared.
excellent, plus
t.
t squared. So right now I have the function of the displacement and the acceleration at any time t. I have a is equal to 60t plus 2, and I have s is equal to t cubed plus t squared. And what I'm asking for, I want you to find the position and the acceleration at time equals 3 seconds. What should I do next? Plug it here. So tell me, what is the acceleration is going to be? 3 by 6 is going to be 18, plus 2 is going to be 20 feet per second squared. And the position is going to be 3 to the power 3 plus 3 to the power 2. 3 to the power 3 is going to be 27, plus 9 is going to be 36 feet. Is it difficult? It's a very easy problem. Let's make it a little bit harder. another example. Says there's a particle. This is the origin. And a particle moves along a horizontal path with a velocity v 3t squared minus 6t. So I give you the velocity as a function in time, and this is meter per second. Pay attention to the units. This was feet per second, this is meter per second. If it's initially located at the origin, so it started from O, determine the distance traveled in 3.5 seconds and the particle average velocity, average speed during the time interval. So at t equals 3.5 seconds, I want you to get number 1, distance traveled, number 2, average velocity, number 3, average speed. One of these 3 quantities. You will tell me it's the same thing. You give me a function, moves along horizontal, start from rest, I guess. Initially located at the origin. Yeah, started from rest. Okay, so at t equals 0, s equals 0, and velocity is equal to 0. You tell me, what is the difference? Do you guys remember? Here I have plus, here I have a minus. Here, I was for sure that the velocity is keep increasing, right? But here, since I have a negative, there might be something happening. At some point, maybe the velocity was going positive, and at some point it might go negative. How can I know this? Like, let's put if time equal to 0, s is going to be equal to 0, and the velocity is going to be equal to 0, because t is 0, v is 0. Let's put 1 second. What is going to happen? You are going to have 3 multiplied by 1 minus 6. So that means that the velocity is negative 3 that way. Put it 2, so it's going to be 3 multiplied by 4 minus, so it's going to be 0. So at 2 seconds, the velocity is going to be 0, and somehow it might change its direction. So you need to capture that, and I will tell you why. First, since I have negative here, I need to find where the velocity is changing its direction. So to do this, the velocity changes the direction when it comes to 0. So you put v equal to 0. So at v equal to 0, what is going to happen? I'm going to put 0 is going to be equal to 3t squared minus 6t. To solve this equation, is it easy to solve? This is t squared, yeah. So I'm going to take 3t as a common factor. I'm going to have t minus 2 equal to 0. So it's either the velocity is 0 at t equals 0 or at t equal 2, right? And that makes sense because the body started at 0 at velocity equals 0, and also the velocity was 0 again at time 2 seconds when t was equal to 2. All right? Okay, so I got the velocity equal to 0. What I'm doing right now, I'm trying to find the total distance that this body did. If you solve the problem right away, okay, I want to find the distance. So I'm going to say s minus s node, the integration of t node to t. So you will find out like that s is going to be equal to the integration of this, which is going to be t cubed minus 3t squared. That's s. It's very easy to do it. But if you substitute with t equals 3.5, like if you find s at time equals 3.5, it's going to end up with 3.5 cubed minus 3 multiplied by 3.5 squared. This is going to give you 6.125 feet. That means at t equals 0, your body was here, and at t equal 3.5 seconds, your body cut distance 6.125. But that's not the total travel distance. Your body did something tricky. It was here, and then went with negative velocity in that direction, and then it changed the direction of the velocity and came here. So if I want to find the total distance traveled, I have to find this distance. At t, s at t equal 2 seconds. So at 2 seconds, you have 2 to the power 3 minus 3 to the power multiplied by 2, which is 2 to the power 2. So this is going to give you 8 minus 12 is going to give you negative 4 meter. That means your body cut negative 4 that way. And then to go from t equal to 2 seconds to here, it makes another negative 4 and 6.125. Did you guys understand this? This is the part that is tricky in this problem. So if you have a negative inside the velocity equation, you have to find where the velocity changes its direction and then calculate the total distance so that you can find the total travel distance. So you tell me right now, is what I did. What is the total travel distance? The body starts at 0, make a distance negative 4, and here cut negative 4 and then 6.125. So it's going to be 4 plus 4 plus 6.125 is going to give you 14.125 meters. That's the total travel distance. If you said that the total travel distance right away by substituting in this equation at 3.5 and you said 6.125, that's not right. That's the change in the position from time 0 to time t. It didn't take into account the negative positive 4 meter that you did. So I got the first one. V average. What is V average? If you guys remember the definition of V average, it was the position number, the final position minus the first position over the total time that you have done. So the final position was at 6.125, right? That's the final position that you have, 6.125. The first position was at 0. At delta t, you did this in 3.5 seconds. When the average velocity, it doesn't matter what the positive, negative distance that you cut. It only matters where you at and where you ended with. It doesn't matter if you go this way and came back to the same position and you cut it that way. The first position and the final position. All right, so this is gonna be 1.75 meter per second. But if I ask you for the average speed, V average speed equal to the total travel distance over delta t. That means all the distance that you cut, which is the 14.125 over 3.5 seconds, and this is gonna give you 4.04 meter per second. Does anybody have any questions? Is it difficult? I don't think so. If you have the equations, if you think about your problem, right now we have two types of problems. One of them that might end up having negative velocities, and there's one that will never have negative velocity. Why? Because every term is positive and the time is never going to be negative. So the velocity is always increasing. Here, maybe, because I have negative component, and the velocity might decrease. So I have to find out where it increased and where it's decreased. And if you want to find out, like if you want to make a graph, let's see, V over time, T and V. So the V here is 0. You will find out it's going negative, this, and then it's going to come back, and it's going to be 0, and it's going to increase again, something like this. Start at 0, and at 1 second, if you substitute here at 1 second, it's going to be 3, 1. So, and this is 6, it's going to be negative 3. And then here it's going to be 0, and then increasing again. So this is how the velocity is increasing over time. So the second topic that we need to talk about chapter 12.3. Erratic motion. So erratic motion, it says when a particle has erratic or changing motion, then its position, velocity, and acceleration cannot be described by one single function. What does that mean? Like, let's say I'm gonna try to capture the velocity with time. Sometimes our motion, like the velocity is increasing, and at some point, the velocity is constant. So if this is the motion, I can describe my motion with one single function. I need to find where my motion is changing, let's say at t dash, and then I'm gonna have a function for the first part of the motion and another function for the second part of the motion. That's what is the erratic motion is. Sometimes it's the acceleration that is changing, it's not constant. So I'm gonna have like something, acceleration is increasing and then it's decreasing like this. So I need to like see where is it changing. I'm gonna have two functions that describe the acceleration over time. But one thing I want you to know, I'm not sure if you have this in your basics or not. The relationship between the velocity and time. Do you guys remember this equation, S minus S naught, the integration of V dt from t naught to t, right? And we have another one for the acceleration, which is V minus V naught. It's going to be the integration of a dt from t naught to t. Do you know if you have a graph that has the two components of the integration, it's both axes. Like if you have v on the y-axis and if you have t on the x-axis, the value of this integration is the area under this curve. You guys know that? The area under the curve between the two variables of the integration is going to give you the value of the integration. Basically, the integration is you take a piece here, it's called dt, right? And you integrate this piece, like you take small pieces and you integrate this piece by piece until you get the full area under the curve. That is the integration. Like you get the area dt, and actually, like let's say what is the area of this part? The base is dt and the height is v, the velocity. If you multiply v dt, you get the area of this part, and if you integrate it from t equal to 0 to t equal to t, you got the area under the whole curve. So you got the value of this integration, right? But the thing is, our function is not constant, so you have to divide this integration into two parts. You have to separate this and get a function for this and a function for this. So this is going to be the integration from t1 to t2 v dt plus the integration from t2 to t3 v dt. So you have to separate these two functions. Well, I'm not going to make it that much complex, but let's see how the problems look like. But you guys understand, if you have the motion, two functions can describe the motion, you need to deal with the two functions separately. All right, so let's see. So this part.
Let's try.
Symbol 12.6. Alright, it says that a bicycle moves along a straight road. So you have a bicycle, I'm going to make it like a bicycle, and it's moving on a straight road. And it says such that its position is described by the graph, this graph. T and S as a function of t, and the units are in feet. So this bicycle, in the first 10 seconds, it was on a parabolic curve like this. And then from 10 to 30 seconds, it was linear, something like this, until you got here, 30 seconds. So the function of this, of the first curve, was s equal t squared, and the function of the second curve, s equal to 20 t minus 100. And this point 500 feet, and this point is 100. Okay. The question is, construct, so right now I'm asking you from this curve, try to build the VT curve and AT curve. Like try to build another curve that shows the velocity versus time and the acceleration versus time. Let's see how we can do that. So first you have two functions. You need to separate them together. The velocity here is different from here. The acceleration here is different from here. Why? Because the position versus time function is different. All right, so let's say I'm gonna make, first I'm gonna solve the part from, let's say 4. For t more than 0 and less than 10 seconds, all right? What is the S? S is equal to t squared. Guys, tell me, how can I get the velocity? What should I do? I differentiate or I integrate? Differentiate. The time rate is change of the position, right? It's going to be 2t. How about the acceleration? It's going to be dv dt, and it's going to be 2. Excellent. So I got the equation of the velocity and I got the equation of the acceleration. Right. Second step, for t, if it's more than 10 and less than 20, what should I do? I'm going to do the same thing. I'm going to get the function of the second motion, s is equal to 20t minus 100. I'm going to do the same thing, ds dt, to get the velocity. So it's going to be equal to 20. And I'm going to get the acceleration is going to be equal to dv dt. What is the value of the acceleration?
0.
0. There's no acceleration. And that actually makes sense. If you have a second degree displacement function, when you differentiate it, it's going to give you first degree velocity, and then you differentiate it, you're going to get a constant acceleration. But if you have a first degree distance, when you differentiate it, you are going to get constant velocity, and the acceleration is 0. This is going to make it easy for me to write or to draw the relationship between the time and the velocity and the relationship between the time and the acceleration. Okay, you guys tell me, how can I do this? Can you draw 2t? And by the way, this at 10 seconds. After 10 seconds, you have to stop this function. All right, let's see what's going to happen. At time equals 0, the velocity is equal to 0. And at time equal 10 seconds, what is the value of the velocity? 2 multiplied by 10 is going to be 20. So, and it's linear, right? Because 2t. How about the acceleration? The acceleration is 2 and it's always constant. Something like this. So I come here, this is 20, and this is 2, and here is feet per second, and here is feet per second squared. All right, so I drew the first part. The second part, the velocity is constant, it's 20. So at 20 is going to be constant until it hits the 30. Here, the acceleration is 0, so the velocity is 20 and the acceleration is 0. So this is going to be all 0 until 30. Is that difficult? So let's see what I did. I gave you a problem. A body is moving with two functions. Each function is described with s function in t squared, s function in t. I separate them into two problems. From 0 to 10, where the function is s equal t squared can be applied, and another one from 10 to 20 where this function can be applied, and solve them separately, and then substitute with the 2 points that I have, 0 and 10, put them here, and the velocity and the acceleration. And in this interval, I have 10 and 30, and then I put them here in this function. And then I draw the two curves. All right, so there's another problem, but I'm not gonna solve it. Maybe I will give you an idea how to solve it. So, by the way, this problem is easy. Why? I give you S, and all what you have done is just a bunch of differentiation. Differentiation is very easy. But what if I give you acceleration, and you have to integrate to get the velocity, and integrate to get the distance? That is a little bit difficult. I'm not sure who likes differentiation more and who likes integration more, but for me, differentiation is much easier. I don't have to substitute with the boundary of the integration and all of this. So right now I give you the acceleration as a curve. And look at this. Can you guys tell me what's happening? It tells you a car in the figure starts from the rest at 0 and travels along a straight track such that it accelerates at 10 meters per second squared. Okay? It accelerates, that means it's positive, and then for 10 seconds. Here, time is equal to 10. What happened after 10 seconds? It accelerate or decelerate? Decelerate, right? Accelerate for 10 seconds and then it decelerate with 2 meters per second squared. Draw the VT and ST graphs and determine the time T dash. I didn't tell you here what is the time T dash, but let's see what I told you how to find it. I'm asking you to determine the time T dash needed to stop the car. So what did you understand from stop the car? What does it mean? What is 0? No, the velocity is 0. The acceleration is the same, but the velocity means a stop is like the velocity is 0. So if you find the velocity function at this part and you put v equal to 0, you will find what is the time t is. But for me to do this, that's actually a very easy problem. I have constant acceleration. That's very easy to integrate because it's not a second degree or a third degree. So I have to divide it in two parts. For t more than 0, less than 10. And for t more than 10 and less than t dash, which I don't know. Okay. I'm not gonna solve this problem, but I'm gonna tell you one trick that you might fall in. Since we are gonna do integrations, we are gonna have a boundary of integration. Tell me, if I'm integrating the acceleration to get the velocity, what is the boundary, the time boundary of the integration? It's from 0 to 10, right? How about the second interval? What is the boundary of the integration? From 10 to t dash, not 0. So the second interval, it doesn't start from 0, it starts from 10. That's the tricky part that you have to put. And it's gonna do the same thing, like if you wanna get the velocity, it's gonna be v minus v node, the integration of a dt from t node to t. And you know that this is 0 and this is 10. And v node is 0, starting from rest. Here is going to be v minus v node equal the integration from t node to t a dt. T node is not 0, that's 10, and that is t bar t dash. And v node is not 0. You need to find what is the velocity at 10 seconds. So you need to find what is the value of this. Same thing with the position. S minus S node, and then you integrate v dt, and you're gonna do the same thing here, and you are gonna draw the graphs. But let's draw the graphs without even by sense. Let's use our engineering sense to draw this graph. Okay, I'm gonna make something like this. Let's say T, E, and I'm gonna make something like this T and S. All right. What do you think here? Is the velocity increasing or decreasing? It's accelerating, right? So the velocity is increasing, so this goes up, right? Until some point, and then decelerating again, so the velocity is going down until it stops, right? So definitely at some point, this is gonna slow until it comes to 0 and stop, right? And what is the time here? It's 10 seconds. The separation from the acceleration and deceleration. So that's how the velocity look like. And it's linear. White's linear. White's not parabolic. This is constant. When you integrate it, it's going to increase 1 degree, right? So if we integrate it again, what is going to happen to get S? Is it going to be linear? It's going to be second degree, right? So you are going to have something that the distance is increasing too much with a second degree, and then another second degree parabolic that way. This one is increasing, this one is decreasing. Okay, so it's gonna be something like this. How can I do it? All what you have to do is to find what is the, after you get the equation of S, substitute that S equals 0 and S equals 10, and maybe 1 point in between, like 5. So you will get 3 points, and then you draw a curve. And then 10, you get 20, and 30, and you get 3 points, and then draw another curve. That's how you solve this problem. Okay, maybe you can check for the full solution here, and I have it also in the notes. I'm gonna upload it today. That is gonna close the part that handle the erratic motion. Okay, so the next part that we have today is so am I too fast, too slow? Definitely not too slow, right? So you need me to slow down a little bit? Definitely. But okay, if I'm fast, I'm recording the class. I'll try to slow as much as I can, but if you miss something, go to the videos and revise, and if you stuck with something, maybe you email me and we can have an office hour and talk together if I'm too fast for you. But I will do my best to slow, okay? The thing is, I want to solve with you as much problems as I can, and I want to give you basics as much as I can. So, by the way, there's things that maybe I didn't talk to you about it. This class has part related to fluid dynamics, so maybe at some point in this semester, there will be another professor for 1 or 2 weeks from the water department. Professor Arturo Leon. He's gonna handle the fluid dynamics part. He's gonna have maybe 1 question in the second midterm, 1 question in the final exam in the fluid dynamic part. And also we are gonna have 1 day that we're gonna go to the wall of wind so that we see how fluid dynamics look like and how real structures get tested. We're not gonna see a full test, but we're gonna see the facility and how it's look like, and there will be somebody tell us how they do testing. And maybe 2 or 3 lectures we're gonna do some structural dynamics so that we see how dynamics application applicable in the structural engineering classes. All right, as I said before, nobody are allowed to be on the phone, so I hope that you guys have this in mind. If you wanna check your phone, I know, go out, check your phone. Here, just like if you wanna listen to the lecture, I'm not taking attendance, nothing. So all what you have to do is just like listen to the lecture. Okay, so right now we finished the straight line motion and the erratic motion that has 2 functions. Now we are gonna take it to the next level, which is what if our body is not moving on a straight line, and that's happened in many applications. Can you guys tell me what kind of applications that we have some bodies that doesn't move on a straight line? Any applications that you are aware of? So if like that's something that most of us do, you are driving on the road in a straight line and somehow you have to take an exit. And an exit, you take a curve. So your car is getting on the curve and is not like a straight line. It's something, a curve with a specific radius. So that's one of the applications that you move on a curve. And there's lots of mechanical applications of curved linear motion. So chapter 12.4, we are going to talk about general curved linear motion. Okay. So let's see that we have a curve like this, and the center of this curve is somewhere here. And you start your movement here. Let's say that you are on the I-75 and you need to take an exit, and you started the curve here. And let's say I captured you here at position R. And right now we're going to talk about vectors. Before we didn't talk about vectors because all the motion are a straight line, so we know where's the direction. Right now everything is going to be vector. So vectors mean that we need to know not only the location, like the position is, like we need to describe it as a magnitude and direction. Where are you at and where are you going? So this is where you started, and let's say this is where you ended. This is R vector dash. Look at this. The change of position is the difference of position between these two, right? And that's what we call delta R. But you didn't move on this line, right? But this is the change of position. But if you want to look at the distance that you travel, is all of this curve. That's what we call S. So right now we are going to have something is called the speed and also the average velocity. So we're going to talk about all the things that we have done last time: position, distance traveled, velocity, and acceleration. So let's find these quantities right now. First, let's talk about the R vector. R vector is the position vector, and it always has magnitude and direction. And sometimes this motion is in the 3D, but we're not gonna study the 3D. It might be 3D or 2D. What we are gonna study is the 2D. We are gonna assume that the curve, it doesn't change in the elevation. But let me ask you, in the real application, it's gonna be 2D or 3D if you are driving your car and exiting a bridge. So the bridge is a higher elevation, and when you exit and want to get to the road, your elevation is getting changed. So that's a 3D motion, right? But we are gonna assume 2D motion here. Okay, so the first quantity that we need to talk about is the displacement, and then the distance traveled. So that's number one. Displacement. Number two, distance traveled. You guys tell me, what do you think? Which one is the distance? Which one is the displacement? Based on our basics from the linear motion, we have two quantities, delta R and S. Which one is displacement and which one is distance traveled?
Displacement is delta R.
Delta R. It's the position number, the final position minus the first position. That's displacement. How much your position changes, or how it changes. It was here and came here. It doesn't matter what path that you take. Like, let's say we're here and here. That is that change in the position. It doesn't matter if you go that way, if you go that way, if you go that way. That is distance traveled. You can travel distance on different passes to get to the same position. So what I'm interested at is the displacement, which is delta R. Distance to travel is S, which is, or delta, let's call it delta S, which is S, the position here. Like if we take this curve and we make it straight, so the S at 0 until the final distance that you did. So that's delta S. All right, so the other quantities that we need to talk about is the velocity, which has many quantities. So we need to talk about instantaneous velocity, the same thing that we did before. Number one, instantaneous velocity. Let's put number two, average velocity. Number three, average speed. Number four, instantaneous speed. Okay, let me ask you, when I say velocity and when I say speed, velocity is going to be related to delta R or delta S. And the speed is going to be related to delta R or delta S, based on our background from the last lecture. So speed is always about the distance that you travel. So if you travel, like if I say I moved from here to this door, if I use the shortest distance from here to here, so my speed is going to be like, let's say I cut this distance in 2 seconds. But if I go all the way to the end of the room and then went back, so I'm gonna take more, so my speed is gonna be less. So speed is related to the path that you take, but velocity, it's all about the position that it changed. So an instantaneous velocity is the time rate of the position. So if you wanna find the instantaneous velocity, which is V, it is the time rate of the change of the position R with respect to the time. Same thing what we did before is the ds dt. The average velocity, V average, it is the final velocity, V final, minus, let's say, V dash, minus the V that you start with. Like, let's say, always the velocity is tangent to the path. Like, if you are moving here, the velocity is something like this way. If you are here, the velocity is here. If you here, the velocity is there. So this is the V that you start with, and this is the final V, V final, let's say V bar. So that is the starting velocity and the ending velocity. So it's gonna be the end velocity and the start velocity, and all of this over the total time that you take from here to here. That's the average velocity. But instantaneous velocity is the velocity at any time, like here. All right, speed. So average speed and instantaneous speed. Let's do instantaneous speed first. Let's say V speed. V S speed. This is instantaneous as ds dt. It's like you take this curve and you make it straight and you see how much the variation in the distance that you are cutting over time. Okay? Like, I might give you the problem, how much S is it changing over T or R is it changing over T. So this is speed, this is position. Average speed, like let's say V speed average, this is gonna be S final, let's say S minus the S that you started with over delta T. So in instantaneous, that means something differentiated with respect to the T. Average is like final minus start over the time T. You are taking an average between two quantities. Like you have 100 and you have 80. So you take the average of 180 is gonna be 90. All right, so that's for the velocity. So let's take it to the next part, which is the acceleration. Acceleration, we have two quantities. We have the instantaneous acceleration, and we have the average acceleration. Same thing, instantaneous acceleration is going to be A, and A is going to be D, V dt, and V is the instantaneous velocity. And this you can write it actually as d squared of the position r dt squared, and we can write it like this, two dots. And this we can write it as r with one dot, and I told you that the dot means that this variable is differentiated with respect to the time. Average acceleration, A average, is the starting acceleration, sorry, the final acceleration, let's say A final, minus the A that you start with over the total time. Oh, no, it's the average velocity. This should be the velocity over time. Here, and this one, sorry. Let's get back to this one. So if something over time, what I want to write here is the R that you start with, the final R minus the start R over the time delta t. Because distance over time is going to give you velocity. Same thing here, velocity over time, you are going to have v final minus the v that you start with over the time t is going to give you the average acceleration. So mostly we are going to deal with instantaneous velocities. Like in most of the application, this is going to show up in the versatile chapter, but other than that, we are going to deal with instantaneous velocity and instantaneous acceleration. Okay? Does anybody have any questions so far? I was doing the same thing that we were doing last time. We are trying to find the quantities, or what we call the kinematics variables, like position, displacement, speed, velocity, and they have the same relationship. You have to differentiate the position to get the velocity. You have to differentiate the velocity to get the acceleration.
Yeah,
Okay.
question.
Yeah, sure.
The delta S is basically the S in the diagram, right? So this is struggle?
This is.
Yeah.
Yeah.
Okay.
What is the question?
No, just making sure that there's no difference between delta S and S in the diagram.
Okay, this is the S on the diagram. It's the same like this one. So that's the S that you start with. Let's say that you start at S equal to 0, and you ended up with here. So it's going to be the final S minus the start S that you have on the curved path, not the change of the position. All right, so that's very good. I mean, like, okay, we know the relationship between the velocity, position, acceleration, and everything. But when it comes to solving problems, dealing with curved paths is a little bit tricky. We have to find a coordinate system that allow us to solve the problem easily. Okay, like let's say that I have curved paths like this. What coordinate system out there that I can, tell me any coordinate system that you are aware of? We have Cartesian. What is Cartesian? X and Y, right? What else that we have? Polar coordinate system, like what is the variables?
Theta and radius.
The radius and the theta. So that's also another coordinate. There's another coordinate system called tangent and normal coordinate system. So there's different ways that we can solve curvilinear motions. The first one that we're going to learn is Cartesian. And that means that we're going to deal with X and Y. Number two, it's called tangent and normal. Tangent, normal. And that can be T and N. I'm going to teach you what this is. And the other one is the spherical or radial or cylindrical. We can call it spherical. And that's R and theta. All right. So let's say that we have a body at this location. And the body at this location, what is the direction of the velocity? And it's increasing. It's gonna, as I said, it's gonna be tangent to the curve, right? So I come to the curve and I take a tangent, and definitely the velocity is this way if it's increasing, and it's the other way if it's decreasing. So I'm just gonna say this is the velocity v. It doesn't matter if you are going to deal with Cartesian, tangent, spherical, R and theta. It doesn't matter. The velocity is going to be always tangent. Versus if you are going to deal Cartesian, so I'm going to have an x-axis like this and a y-axis like this, and this is where my body at. So what I'm going to do . If I want to describe the position, so I'm gonna take the origin and try to make a line, draw a line from the origin to the body. And that is the position, the instantaneous position of the body. Are we agreeing on this? That is the instantaneous position of the body, R, right? If you are gonna deal with this as Cartesian, you can make R as two components. So you can have it as Rx and Ry. And for the Cartesian, so I'm gonna put the Cartesian system only today, and maybe we continue with other system next time. So let's say or so right now we said that the position of the instantaneous position of the body R vector, we can describe it Cartesian Rx and Ry. So I'm gonna say it's Rx in the I hat direction plus Ry in the j hat direction. Do you guys know what is I hat and j hat? If you don't understand what is this is, let's say that you have a body was here and moved to here, cut all this distance. If this distance is 5, the thing is, it is not that way, always that way. It's always like tell you that your body cut this distance like, I don't know, 4 in the x direction and 3 in the y direction. Like let's say this is 4 and this is 3. And it did this in the positive x and then in the positive y. So basically, if you want to describe this, you can say if the body moved from point A to point B, but it did it ACB, so how we can describe it, we say that AB vector is 4 in the I hat and 3 in the j hat. That means like 4 units in the x direction and 3 units in the y direction. This is how we can describe vectors. Alright, so I have Rx and Ry. How about the velocity? The thing is, the way that I drew the velocity here, it's not in the x and the y direction, but this is the actual velocity of the body. And if I want to convert it to a Cartesian, I have to do analysis, like I have to find the component in the x and component in the y. How? You need to find what is the theta for this velocity is, and then find the components. Find the component in the x direction, like any vector, you can find the component in the x and the component in the y. That's what I want to do here. I want to find what is the component of the velocity in the x and what is the component of the velocity in the y. So I can get vx and vy. You guys tell me, I want you to tell me, how can I get the component of vx and vy? Like if you know that this is v, and you know this theta is like 30 degrees, and I want to get vx and vy. What is the value of vx? It's going to be v cosine theta. And this one is going to be v sine theta. So you can get the two components the way that I got them here. And then you are going to have here v equal to vx in the I hat direction plus vy in the j hat direction. Same thing with the acceleration. Let's say that the acceleration of this body is something like this. A. I need to do the same thing. I need to get the ax and ay. So the acceleration is going to be ax in the I hat direction plus ay in the j hat direction. So that's a little bit of a brief about how we can solve the curvilinear motion, but I'm going to tell you a hint about how to use different coordinate system, like when should I use Cartesian, when should I use tangent and normal. So usually I use Cartesian when the problem has gravity, like a body's falling from the sky or a balloon is going to the sky. So if there's a gravity, and always the gravity is in the vertical direction, in the y direction. So it is always, it's better to use Cartesian coordinate system. But if you, tangent and normal is always good when you have a body that is moving on a horizontal curve, like a car or something. So it's better to use tangent and normal. The cylindrical is when you are sure that the curve that you are moving on is a circle. Like a bar is restrained and is going to move in a circle. We're going to see this in real problems. We're going to spend, I don't know, maybe 2 lectures finishing Cartesian, tangent, and cylindrical, maybe 2 or 3 lectures. So we're going to take it step by step. Next time we're going to take it from here and start solving problems. right? Does anybody have any questions so far?
What did you say the tiny normal was used for?
If a body is like a car is moving on an exit or something, on a specific path, and I give you what is the path is. So I know that the car is attached to the path. There was a question here.
No, I had the same question as him.
Oh, okay. It's here in the notes, and we are gonna, in details, take every coordinate system and solve at least 2 problems with each one, so you'll know which one to use in which problem. Okay? All right. See you guys next time.
Carried over.
Sit in a car for 20 minutes. And then we can go home after work. Or an office. Let's go office chair. I know, man.